all of you. Today's topic is silicon lattice constraints and structure of interference status. Subtitle: Understanding the influence of crystal structure and electronic defects. Hi, my name is P. Saicharan. I am from Data Science Department. Introduction: What are interfaces states? Important in semiconductor devices. Examples: MOSFETs. Third one, role of the silicon lattice structure. Silicon crystal lattice overview. Diamond cubic crystal structure. Atomic arrangement in crystalline and coordination sp3 hybridization. Here we are seeing down the definition crystal surface. There are diagram unit cell. This is unit cell diagram. Introduction, we can see what are interface states as questions. This first one, states that appear at the interface between silicon and another method. Localized electronic states with the band gap arise due to the broken or disturbed bonds. Next, formation of mechanisms of interface states. Dazzling bonds, lattice mismatch, oxide defects, impurities, and contamination. Silicon lattice constraints. Crystalline order restricts possible atomic arrangements. Second one, limited flexibility in bonding angles, 109.5 degree Armstrongs. Third one, constraints affects how strain is relieved at interfaces, types of defects that form. Now we can see silicon's definition is silicon's diamond cubic lattice structure imposes fundamental constraints on the electronic properties interface states by dictating the geometry bonding and electronic orbitals of atoms at the boundary. The termination of this regular tetrahedral lattice at an interface such as with silicon dioxide SiO2 inevitably leaves unsaturated covalent bonds known as dazzling bonds. We can see in the second third slide which are the primary origin of these interface states. Definition of interface states. An interface state is an electronic state with an energy level located with the semiconductor's band gap. The states are localized at the interface between a semiconductor, example silicon, and another material, example an insulator or metal, because they can trap, emit, and recombine charge carrier electrons and holes. Interface states degrade the performance of semiconductors devices like MOSFETs by causing instabilities in the threshold voltage and reducing Indian mobility. Silicon lattice constraints on interface state structure. Tetrahedral bonding. Tetrahedral bonding. In a perfect bulk silicon crystal, each silicon atom forms four sp3 covalent bonds with its neighbors, with its neighbors, resulting in a stable, energy minimizing structure. At an interface, the crystal's periodic arrangement is broken, leaving some surface silicon atoms with only three bonding partners. The remaining sp3 orbital with its unpaired electron becomes a highly reactive dangling bond. Electronic levels. A neutral dangling bond creates a defect state near the middle of the silicon band gap. These are known as PB centers at the Si and SiO2 interface. The dangling bond has an amorphic nature. It can be positively charged or neutral one electron or negatively charged two electrons, corresponding to donor and acceptor energy levels within the band gap. Structural defects in addition to dangling bonds, that is and can produce other interface defects, including vacancies, missing silicon atoms in the near interface region. Mitigation strategies. Thermal oxidation passivates dangling bonds. Hydrogen annealing H terminates dangling bonds. High K dielectrics and interface engineering. Consequence lattice constraints. The defining contrasts for profound effects on device physics. Fermi level pinning. A high density of mid-gap interfaces states then pin Fermi level at the interface, making the surface potential of the semiconductors less sensitive to an applied gate voltage. This effect limits the range of a transistor operation and makes device characteristics depends on the interface quality. Surface bending. Damping bond states create charge at the interface, which can cause the semiconductor's energy bands to bend up or down near the surface. This effect can lead to the formation of compression or accumulation layers and affects the electrical response. Definition of lattice points. A lattice point is an imaginary point, a three-dimensional array crystal that represents the position of an atom, ion, or molecule in a crystalline solid. Points are arranged in regular repeating pattern, and each point has an identical environment defining the structure, the crystal. The arrangement of these points is what gives a crystalline material its characteristic properties. What is the lattice structure of silicon? Silicon is a diamond cubic structure where each silicon atom is tetrahedrally bonded to four neighboring atoms. This structure is based on a cubic FCC lattice with two atom bases and results in a stable rich lattice. The lattice constant or the distance between atoms in the unit cell is approximately 5.43 angstroms or 0.543 nanometer. Bonding each silicon atom has four valence bonds and forms four covalent bonds with its neighbors, a result of forming a hybrid orbitals. Structure. The structure can be visualized as two interpenetrating FCC lattice. Each atom is bonded to its nearest neighbors at an angle of 109 degree 5 angstroms. Properties. The diamond cubic structure interesting material acting as an insulator at absolute zero but conducting electricity at higher temperatures or when doped with impurities. Conclusion. These constants govern how interface states form, essential for improving modern semiconductor devices. A single unit cell of silicon contains 8 atoms. A lattice structure is a A repeating pattern of points or objects that can be found in material science, like in the arrangement of atoms in a crystal, or in engineering as a 3D printed lightweight cellular structure.